Hi, everyone. My name is Bijit. I'm currently working with Miho. So uh, I am interested in like these field link bound states, not like destroying them or something, but I want to study whether we can do some optical manipulation of those field link bound states. So we know about the polar molecules. They are prone to collisional loss when they are inside an optical dipole trap. And we have heard about that shielding methods can protect them from loss. So they can be either by static electric fields, microwaves, and even lasers. So what a typical potential in presence of shielding looks like, I have chosen a I've chosen a molecule. Yeah, so which has relatively very high dipolar, lithium cesium, and in presence of some electric fields, it will show this shielding effect at very long range with a barrier. Now, if we zoom in at this region, we will have this dipolar attraction at even longer range, as we have just heard, and they will accommodate bound states. And these are called like field link bound states. And we have just heard from Jeremy and Thais that these are basically due to the long range attraction and the shorter range repulsion that actually creates this potential well. Now, this field link bound states were actually quoted by John Bone and his group. So they were proposed like 20 years, more than 20 years back, and recently they have been observed. So for shielded molecules, like fermionic shielded molecules. Now, my question is whether we can use these weakly bound field linked states to actually create stable polyatomic ultracold molecules. So that's something like an ambitious question, but I don't know whether we can do. But let's start what we have. So my goal is actually to do something like of a stirrup, which is very successful for preparing diatomic molecules, starting from weakly bound fetchback states and going via an intermediate excited state, coming to a ground state. And we are also interested in whether we can actually do something similar like photoassociation. I mean, like photoassociation of colliding atoms, which actually get into a bound state in the excited electronic state. So now we have molecules other than atoms, and we choose an excited state of the molecule here, which is like a B triplet pi. And B triplet pi of I am considering alkali dimers to start with, and B triplet pi is metastable because it has a very weakly allowed transition with the ground electronic state due to the spin forbidden transition, but it has a weak spin orbit coupling with the nearby A singlet sigma state, which actually makes it allow, but with it's actually very small line width. And so the lifetimes of these states are about few to tens of microseconds. Now, it has also similar rotational constants and dipole moments, but not exactly the same. So I mean, what we want to actually look at is whether we can observe these field link bound states and shielding in an excited electronic manifold like X plus B. Why I am looking into this? Because let's say we have an intermediate state that is controllable. It is polyatomic. It's like a 4-atom system, and we have loads of loss channels. So I want to actually try to isolate one state which is controllable with the external field and which is embedded in the long range, so that we can have some Frank-Condon overlap with the starting field link states in the ground state. So of course, these states are metastable, and these have a lifetime, but we actually approximate that the lifetime of the field link states are fully determined by the lifetime of the B molecules. So we should also we should be careful about that this structure in the B triplet pi, which has a spin orbit coupling, which has the spin and the orbital angular momentum, and and there are like the spin couplings and and there are hyperfine couplings. But these additional components here are like 100 wave numbers above, and even with the lowest omega state, which we actually consider here, the omega equals to 0 plus, omega is the projection of the total angular momentum on the bond axis. There are different parity states, but they are also separated by a few wave numbers. So we considered the few lowest rotational levels of the lowest omega component, omega equal to 0 plus of triplet pi, so triplet pi 0 plus, and only look at the few rotational levels, and to a first approximation we ignored the structure of the B triplet pi, the other components. So, and we only consider as a spinless structureless molecule with a different dipole moment and rotational constants. So we calculate for different alkali, we consider different alkali dimers, also some similar molecules like silver molecules, which can be considered a pseudo alkali dimer. We calculate the rotational constants and dipole moments for the B state of the molecules, because they are not available experimentally. And we also calculate the transition dipole moments between the X to B transition. And the spin orbit splitting, so that we are sure about how much difference of how much the spin orbit components are actually far away from the rotational the B triplet pi state, the P triplet pi 0 plus state. So what do we know about the static field shielding scenario? So what I am considering here is like static field shielding, or a static field shielding in the ground state, and whether we can actually get the scenario in the excited X plus B manifold with the same electric fields. So in the lower panel, we see that the lines actually cross, as shown by Jeremy, as a function of electric field, as a function of some reduced electric field. And if your electric field is above the crossing point, you will have the shielding in the upper state in the red threshold. But if you look at the upper panel, where the two molecules are in different electronic states, they have different rotational constants, and that's why their structure is different. They have additional lines because they have different rotational ladder even at zero field. So the physics of shielding will be different there. The upper threshold, the red one in the upper panel, will have a dipole-dipole repulsion due to the blue one at almost all fields, even up to higher fields, so at zero, including the zero field. So that's different physics which is going on. So we consider one electric field where X plus X is shielded, and the lower panel shows that the potential is a repulsive at some electric field, and we have the inset in the lower panel shows the long range dipole, or a long range potential well that can actually contain the bound states. The upper panel also shows the repulsion in the higher threshold, the red threshold, and we'll have the dipolar attraction at the even longer range, and we'll have the long range potential well that can accommodate bound states. Now we should be careful about the dipole repulsion, or the dipole interaction in X plus B, because there is an additional term. There is a resonant first order dipole interaction term as well, which will be proportional to the transition dipole moment. Even it is smaller, but it is still there. It is not negligible. So that gives a deeper potential well in the X plus B, and we actually calculate some two-body scattering properties for both X plus X and X plus B. Interestingly, you can see that in X plus B, in the upper panel, the black curves are the loss, correspond to the rate coefficient corresponding to the loss processes, and they are suppressed at quite an extended region of electric fields. And if we zoom in around the lower field, at very low fields, there you can see there is a suppression of loss even at close to zero field, and that's due to the unique property of this different thresholds due to the different rotational levels. Obviously, they are limited by one body loss due to the B molecules, but the two body losses are suppressed. And in X plus X, we have the usual picture, like we have this, they are protected by the shielding in for at some finite electric field. So we can work at a common window where both the X plus X and X plus B are shielded as a two body loss. So we calculate the bound states. I take an example for a typical molecule, lithium cesium, which is very high dipole moment, and we calculate the bound states in both X plus X and X plus B. The dashed black line show the bound states for the ground state, X plus X, and the colored lines show the bound states in X plus B. And we can actually propose some proof of principle experiment in the long range, where we can actually go from a shallower state in X plus X via an intermediate state in X plus B and come back into a deeper state in X plus X. And we calculate the Frank-Condon factors in the lower panels. This dash dot and the dashed lines actually correspond to the different lines of the binding energies. So this is doable, and this is quite tunable with the electric fields, as we see here. Also, we can do some photoassociation. We can propose some photoassociation experiment where molecules colliding in X plus X can be photoassociated to fielding states in X plus B. And we see results for different molecules. We consider here rubidium cesium and lithium cesium. Now, rubidium cesium is not so dipolar, but even if that, the X plus B, the well in the potential well in the X plus B is quite deep for rubidium cesium, and it can accommodate bound states. Now, we have to be careful that the widths, the line widths of the B molecules are around like a few tens of kilohertz, and the binding energies are of the order of megahertz, and that's why we get resolvable photoassociation lines. But since these are very, very weak transitions, the intensities are very weak, around 1 microwatts. I don't know whether this is realizable or not. So what our results provide are the first steps. This is very initial, very small step, but we think this is important step towards some spectroscopy of fielding states, and whether we can move forward to getting towards stable polyatomic molecules in the ground state. So of course, we will extend the theory with microwave, which will give more tunability, and which will allow more fielding states in the X plus X state for different molecules. And our ultimate goal will be to actually somehow go towards the short range region of the molecules, so that we can have a Frank-Condon overlap between the bound states. And this is work under progress. Thank you. So yeah, I want to thank you, Miao Tomza and his group, and the funding organizers.
Yes, time for questions.
By fielding state, you mean microwave fielding state here, or DC field link state?
So I have shown here results for DC field shielding, but this just applies to fielding states by either microwave or.
But this is also applicable to other dipolar molecules, like you show lithium cesium, which is, I guess, the best dipolar molecule. But yeah. Is it universal with other molecules or less universal than?
No, it's universal with other alkali dimers.
Even so, okay.
So for static field shielding, we need quite high dipole moments for the fielding states to exist, but you can tune those with microwaves for lesser dipole moment molecules, and you will have the fielding states as well.
Okay.
In the other molecules.
Thank you.
The idea here was that we need at least 2 bound states in the ground to make stirrup. So then we are restricted to only few the most dipolar. Yes, next question.
Thanks for a really nice talk. For the shielding in the mixed state, how does the shielding depends on difference between the constant, between the rotational constant?
Yeah, so this is the rotational constant is some fraction of the difference in the energy difference between the two levels is a fraction of the rotational constant. Here, lithium, I have shown here a result for lithium cesium, which is like 50% of the rotational constant in the ground state. But for different molecules, it could be much, much smaller, and that will give a shielding interaction even at zero field.